Hello students, welcome to our YouTube channel Experience Tutor. Today we'll discuss class 11th physics get more than 95% marks series. Today's lesson is system of particles and rotational motion, chapter 7, ncert line by line, part 4. Before we begin, if you have not yet subscribed our channel, please subscribe it and please like our videos and share it among your friends and relatives. Please click on the subscribe button to support us and please click on the bell icon to get notification whenever a new video is uploaded by us so that you will not miss any of the important video lessons. Let us begin today's class. So today we'll start with 7.5 vector product of two vectors. In last lesson we have studied about the scalar product of two vectors. So work is defined as the scalar product of two vectors, vector quantity, force and displacement. In the last chapter we have done that. We shall define another product of two vectors. This product is a vector. Two important quantities in the study of rotational motion, namely moment of force and angular momentum. Are defined as vector product. So definition of vector product. A vector product of two vectors A and B is vector C. Such that magnitude of vector C is equal to AB sine theta, where A and B are magnitudes of A and B, vector A and vector B, and theta is the angle between the two vectors. C is perpendicular to the plane containing A and B. If we take the right hand screw rule with its head lying on the plane of A and B and the screw perpendicular to the plane, if we turn the head in the direction of A to B, then the tip of the screw advance in the direction of C. The right hand screw rule is illustrated in figure 7.15a. So let us see this right hand screw rule. So say this is the screw which is perpendicular to the plane of A and B. A and B are two vector quantity lying in the plane AB and their angle between them is theta. Now screw is moving towards this direction. So it will advance towards this direction. So if we now in figure B will explain the right hand thumb rule. So we'll imagine in such a way that all the other fingers except thumb is wrapping towards the screw or towards the perpendicular towards the axis perpendicular to the plane AB. Then The thumb is directing towards the is the direction of C. Thumb is in the direction of C. So we can write A cross B. We say it cross. A cross B is equal to A magnitude of A, magnitude of B, and sine theta. Theta is the angle between A and B vector, and we take a unit vector which is perpendicular to the plane of A and B. In this way, we represent the vector product. Now, let us see what is written in the book. Alternatively, if one curls up the finger of right hand around the line perpendicular to the plane of the vector A and B, and if the fingers are curled up in the direction A to B, then the stretched thumb points to the direction of C. Same thing what we have discussed as shown in the figure. Now let us move forward. So here we have studied mainly the screw rule and right hand thumb rule. Both are same, only different representation. A simpler version of right hand thumb rule is the following. Open up your hands. So this all are explanation of right hand thumb rule, just wasting time. Let us because we have already done it. It should be remembered that there are two angles between vector A and B. In figure 7.15, A and B, they corresponds to theta and 360 degree minus theta. While applying either of the rules, above rules, rotational rotation, the rotation should be taken through a smaller angle less than 180 degree between A and B. So we'll take the smaller angle, not the bigger angle. Because of the cross used to denote the vector product, it is also referred as cross product. Note that scalar product of two vector is commutative as said earlier. A dot B is equal to B dot A. But vector product, however, is not commutative. That means A cross B is not equal to B cross A. The magnitude of A cross B and B cross A is same, that is AB sine theta, AB sine theta. But both of them are perpendicular to the plane of AB. Also, both of them are perpendicular to A and B, but vector A and B. But the rotation of the right hand screw rule in case of A cross B is from A to B, whereas in case of B cross A it is from B to A, which means two vectors are opposite in direction. So they are A cross B is equal to minus B cross A. Another interesting property of a vector product is its behavior under reflection. Under reflection, that is, on taking the mirror image, we have x tends to minus x, x tends to minus x, y tends to minus y, tends to minus z. As a result of all components of vector change sign, and thus A tends to minus A, B tends to minus B. What happens if A cross B is under reflection? Under reflection. So A cross B tends to minus A cross minus B, that is A cross B itself. Thus, A cross B does not change sign under reflection. This is an important question for objective, which will be asked which can be asked in any of the exams, NEET, IIT, or even in your class exams, final, or any other engineering or medical college examinations. Next thing is both scalar and vector product are distributive with respect to vector addition. So A dot B, B plus C is A dot B plus A dot C. A cross B plus C is equal to A cross B and A cross C. So vector product does not follow the commutative law, but it follows the distributive law. We may write C is equal to A cross B in the component form. From this, we first need to obtain some elementary cross product. A cross B is equal to 0. 0 is null vector and a vector with 0 magnitude. So what is null vector? A vector with null or 0 magnitude. This follows since magnitude of A cross B is A square sine 0, that is 0. From the following, from this follow the results. I cross I is equal to 0, J cross J is equal to 0, K cross K is equal to 0. So remember this. Why this is 0? A good question. So normally if we write I cross I, we can write I vector cross I vector, then say unit vector. Then what we have to write? Magnitude of I, magnitude of AB sine theta to magnitude of sine theta. Sine theta is here 0 degree. So sine 0 is 0. So whole figure comes to 0. Why 0? Because same line. If this is I, then another I is also this over this line. So what is the angle between these two? The 0 degree. So sine 0 degree is sine 0 degree is 0. So anything multiplied by 0 is 0. So whole of this term turns to 0. So I cross I is 0. Similarly, J cross J is 0. K cross K is 0. And this way it goes on. Second thing, I cross J is equal to K. So again, uh, I cross J. So here the I represents the x-axis, J represents the y-axis. So what is the angle between this x and y-axis? It is 90 degrees. So what can we write? Modulus of I multiply by modulus I cross J, we can write a modulus of I multiply by modulus of J multiply by sine 90 degree. Sine 90 is equal to 1, so modulus of I is equal to modulus of J, and modulus of unit vector is 1 into 1, that is 1. Now for K, but the direction is perpendicular to the plane of the x and y axis. So this is I unit vector, this is J unit vector, and in this perpendicular, so in this way, or you can write it in this way. So this is x, so this is I, this is J, and this is K unit vector, which is perpendicular to this plane. Now the thing is that we have proved that I cross j is equal to k. Similarly, j cross k is equal to I and k cross I is equal to j. So how to remember? Draw a circle. Write I, then write j, then write unit vector, and then write k. So how will you remember? I cross, start from here. I cross, after I it is j, it will be k. Similarly, if you start from j, then you can write j cross k is equal to j cross k is equal to I. In this way we can remember this. So I cross and j cross, if we start from j, so j cross k is equal to I, and if we start from k, k cross I is equal to j again. In this way we can remember it. Now j cross I, if we move this direction, then it will be negative. So j cross I is equal to negative k. K cross j, which direction we are moving? K cross j, clockwise we are moving. Clockwise we have to give a minus sign. So minus I. And I cross k, I cross k again clockwise. So again a minus sign, that is minus j. So if we ultimately want to write a cross p, we can write axi plus ayj plus azk. This is a as a whole. B is this bxi plus byj plus bzk. If we do the cross multiplication of a of this and this, we get axby k a minus ax bz z. So how we are getting this? This is simple. First we'll multiply this one with this whole thing. So axi multiply by bxi. Now I cross I is 0. So this whole term, first term, is 0. So we have not written. Again we'll multiply axi byj. So if we multiply axi, the first term, with the whole bxi plus byj and bzk, so is equal to, if we multiply this and this, what we'll get? Ax bx I cross I cross I is 0. So this whole term becomes 0. So we have not written this one. Next is we'll multiply this with this. So it is ax I ax by. First we'll write this, then I cross j. I cross j in this circle, I cross j is k. So we can write ax by k. Similarly, the last thing will multiply here. So, first we'll write this statement ax by k. So if you see here, axbyk is the first sentence, first uh, product of what which we have written. We have not written this 0, this axby I cross I, that is 0. Now the next thing, axi is multiplied by bzk, so we can write the next term as ax bz, ax bz, I and k, I cross k, I cross k. I cross k can be written as, check the circle, ax bz ik, where I and k, it is moving in the reverse direction, so it is minus j, it is minus and j. The same is written second statement, that is minus axz bz j is the second statement. So in this way, similarly we'll multiply this with the whole of this. Again, third statement will multiply these with the whole this, as we have done here. I have shown you with one, just you can multiply so that you'll get this whole line. Now in this line, once we get this, we can take common, I common, j common and k common. So this is along x-axis, this is along y-axis, and this is along z-axis. We have used the elementary cross product in obtaining the above relation. The expression of A cross B can be put in a determinant from which it is easy to remember. So in determinant form, we can represent A cross B, that is ijk ax ay az and bx by bz. So if we solve it, we'll get the same value here. Now let us solve one problem of this type. Find the scalar and vector product of two vectors, A is equal to 3i minus 4j plus 5k and b is equal to minus 2i plus j minus 3k. Now A cross B. So there is a printing mistake here. A cross B, vector A cross vector B, here also cross. So same way, what we'll do, we'll multiply this with the whole of this. Again we'll multiply this with whole of this. Again third, you will multiply this with whole of this. So ultimately, after solving it as we have shown here in the same way, so upon solving we got the answer minus 25. Please solve it on your own in rough and check whether it is coming or not. Then you proceed further. Now A cross B, okay, another way, in the determinant they have given A cross B, ijk 3 minus 4 5 minus 2 1 minus 3, and upon solving we get this one 7 I minus, so this is the vector cross product, and this value is the dot product, so it is not a cross product. A dot B, this is the dot product, this is the dot product. So dot product will not do in this way. Dot product we have explained in the last lesson. In that we will do the dot product. And the cross product as we have explained here, we'll do it cross product. And b cross a will be just opposite. You have to multiply this whole by minus sign. Whatever the answer will you will get, that is b cross a. Now let us move to the next topic, that is 7.6, angular velocity and its relation with linear velocity. Angular velocity and its relation with the linear velocity. In this section, we'll study what is angular velocity and its role in rotational motion. We have seen that every particle in a rotational body, in a rotating body, moves in a circle. The linear velocity of the particle is related to the angular velocity. The relation between the two quantities involved a vector product, which we learned about in the last section. Let us go back to figure 7.4. So this is the figure 7.4. Let us review the figure again. A rigid body rotating about z-axis, each point of the body such as P1 or P2 describes a circle with the center C1 and C2 on the axis. The radius of the circle is R1 and R2 or R2 in the perpendicular distance of the point P1 and P2 from the axis. A point on the axis takes like P3 remains stationary. Fine. Now let us move to the paragraph. The As said above, in the rotational motion of a rigid body about a fixed axis, every particle of the body moves in a circle, which lies in a plane perpendicular to the axis and has its center on the axis. In figure 7.16, we redraw the figure 7.4, showing the typical particles at point P of the rigid body rotating about the fixed axis taken as z-axis. So let us see, we have redrawn the figure. So we have drawn only one circle here. So this P particle is rotating in a circular form in this direction. Its center is C, which is making delta R, which the position vector is delta R. Here its velocity vector is v at P, and it makes an angle delta theta after dt time, after a time dt. So what we mean to say is the circle with the center C on the axis, the radius of the circle is r, the perpendicular distance of the point P from axis. We also show the linear velocity vector v of the particle at P. It is along the tangent at P to the circle. Let P be the position of the particle after an interval of time delta t. So P dash be the position. So after time delta t, the object moves from P to P dash. This is P dash, which makes an angle delta theta, and time taken to do this movement is delta t. The angle PCP dash describes the angular displacement, and angular displacement is delta theta of the particle at time delta t. The average angular velocity of the particle over the interval delta t is delta theta upon delta t. As delta t tends to 0, that is, takes smaller and smaller value, the ratio of delta theta upon delta t approaches a limit which is instantaneous angular velocity, and that is delta theta upon delta t, the particle at position p. We denote the instantaneous angular velocity as omega. We know from our studies that circular motion that the magnitude of a linear velocity v of a particle moving in the circle related to the angular velocity to the particle means we know that this relation v is equal to omega r. So v is the linear velocity, omega is the angular velocity, r is the radius of the circle. We observe that at any given instance, relation v is equal to omega r applies to all the particles of the rigid body. Thus, the particle at a perpendicular distance r from a fixed r1 from a fixed axis, the linear velocity is given by v vi is equal to omega ri. Omega is equal to delta theta upon delta t. This is equation 7.19. So angular velocity is delta theta upon delta t, and the relation between the linear velocity and angular velocity is v is equal to omega r. We therefore refer to omega as angular velocity of the whole body. We have characterized pure translation of a body, all parts of the body having the same velocity any instant of time. Similarly, we may characterize pure rotation by all parts of the body having the same angular velocity at any instant of time. Note that this characteristics of rotation of a rigid body about the fixed axis just another way of studying section 7.1. So here if we see this figure, this is the diagram, this is r, this is ri, and this is the omega in this direction, this is v, and we can write v is equal to linear velocity is equal to omega cross r, vector product of omega r and r. So from the figure, omega cross r is equal to omega into OP. Instead of OP, we can write OC and CP from this figure. Instead of OP, why you have written OP? Because OP is the radius, and OP is equal to what we can write? OP is equal to OC plus CP. Then omega into OC is equal to 0 as omega is along OC. Therefore, omega cross R is equal to omega into CP. The vector of omega and cross CP is perpendicular to omega, that is to CP, z-axis. Also, the radius of the circle described by the particle at P. Therefore, omega cross Cp is equal to omega into Cp. Since omega and Cp are perpendicular to each other, and Cp we can denote Cp by r perpendicular, not by r. we denoted earlier. So omega cross r is the magnitude of omega perpendicular to r and is along tangent of the circle which described at P. Therefore, the linear velocity v at P is same magnitude and direction. Thus, v is equal to omega cross r, which is equation 7.20. For rotation about the fixed axis, the direction of the vector omega does not change with time. Its magnitude may, however, change with instant to instant. For the more general rotation, both the magnitude and direction of omega may change from instant to instant. So let us do till here today. So let us recapitulate what we have done today. Today we have started with the vector product first, and a cross b is equal to ab sine theta, and different derivations of vector product we have done. We have done few sums of vector product. Then we have came with angular velocity and relation with between the angular and linear velocities. Then we have derived an expression v is equal to omega r, which is an important question. Which so you have to write the answer. If they ask to prove v is equal to omega r, then you have to draw this figure and you have to write the expression details which are written here. This is the figure to prove v is equal to omega r, omega cross r, vector product of omega and r, and this is the derivation. This is an important question which can be asked in your class exams, and the numericals and concept can be asked for NEET and IIT and other entrance examinations. Don't worry, we have different tutorials for IIT, NEET and etc. So we'll go through those tutorials for the details of IIT and NEET. So for today, let us finish till here. So let us skip till here for today's class. Please subscribe, like and share our channel. If you have not done yet, please like our videos and share with your friends. Thank you for your support and watching our videos. Thank you very much. Keep watching.